Well, welcome to a short video segment in which I'm going to try to describe the basics of electric potential energy. This is going to serve as a foundation for our understanding of electric potential, which is an important characteristic in electrostatics. It's related to electric fields and electric forces, which you've already studied. An important characteristic to know about electric potential energy is that, just like gravitational potential energy, it is always associated with at least two different objects, in this case electric charges. Just like we couldn't describe the potential energy of a person without thinking about the fact that the Earth has to be present as well, we also can't describe the electric potential energy of, say, a single proton. So in this figure here, we could describe the electric potential energy associated with the 2-point charges, a negative 3 microcoulomb charge and a positive 3 microcoulomb charge. Now, the way we describe it physically is electric potential energy is the opposite of, or the negative of, the work associated with putting this collection of charges together. So we imagine the charges start out infinitely separated, and then we're going to put them in the orientation that they are here. Notice they're 4 meters separated from each other. Now, to move the first charge, I'll just say we move the negative 3 microcoulomb charge first. It's not going to take any work at all, because there are no other charges present. We just have to imagine there's nothing present in the universe except this single charge that we're moving into this position here at x equals negative 2. Now, to move charge B in after that is going to require some work. And in this case, the work associated with collecting them together is going to be positive. And that's because, notice charge A is a negative charge B is a positive charge. That means they're naturally going to attract one another. So when we have a force of attraction, as we move objects closer together, in that situation, the force and the motion are both in the same direction, which means there's positive work done. And if there's positive work done, that means we lower the potential energy. Just to use a gravitational analogy, if I take a book and lower it from a high shelf to a lower shelf, in that case, the gravity is pulling downward on the book, while the motion of the book is also downward. That always means positive work is done, and we have lowered the potential energy of the book, Earth, system. Now, in this situation, it's a little troublesome to talk about how much work is done by charge A pulling charge B towards it. And that's because the simplest definition of work is described as the amount of force that the object is exerting times the little displacement that the object has while that force is being exerted. But remember, with gravitational forces as well as electric forces, the force is dependent on where the object is. So when the object starts far separated from the other, there's very little force involved. But as they get closer and closer, that force goes up. It's an inverse square type relationship. And that means we can't use this simplistic definition of force. So instead, we're going to have to use an integral. And so we're going to write, instead, this work is the sum of a bunch of little work values, all found by taking the force at a specific location and multiplying it by a small little step that object takes at that location. And when we sum up all of those work values from the initial location to the final location, we'll put those in as limits on our integral, then we get the total amount of work done in moving those together. So what we're going to do here is we're going to substitute in the Coulomb force, and we will integrate that over the entire distance that the object moves. Remember, in this case, we're moving object B from infinity to the location here 4 meters away from object A. And when we do that, we're going to get what you're probably going to want to call a formula, but I'm just going to call almost the definition of electric potential energy associated with two objects that are separated by a distance r. When we express the potential energy as the opposite of the work done, here is the relationship that we'll get. We integrate the Coulomb force over the entire distance, and I'm going to use R as the separation distance that the two objects end up being, and that is the relationship that we'll use. So again, if you want to call it an equation or a formula, I guess that's okay, but it really is the definition of electric potential energy associated with two charges, I just call them Q1 and Q2, that are separated by a distance r. Notice in this case, it's very similar to the gravitational potential energy form, except in that case we had the constant big G rather than the Coulomb constant K. We also had masses 1 and 2 that were separated by a distance r. And in that situation we also had a negative sign. We do not include a negative sign in this relationship because the charges themselves can have negative signs associated with them, and that will take care of any appropriate sign that we need on potential energy. Just looking at this situation here, one of our charges has a negative sign on it, the negative 3 microcoulombs. The R would be the 4 meters of separation. So in this case, plugging those values into the potential energy equation is going to give us a negative value. Now, does it make sense that it's a negative value? Well, I'm going to go back to what I said a few minutes ago. When we have charges separated infinitely apart, we're going to define that as no potential energy. And in this case, we have two oppositely charged particles that are closer together. Well, that is definitely a position they would rather be in because they are attracted to each other. So because they would rather be in this position, we call it a lower potential energy state. And how do you get lower than zero? Well, you have to create a negative value. We did it for gravitational potential energy as well. In that case, we always had negative potential energies because masses are always attractive to each other. In electrostatics, we can have negative potential energies, as we do here, but we could also have positive potential energies, which would be the case, for example, if we had two negative charges or two positive charges nearby each other. Just as we can have gravitational potential energy associated with more than two masses, we can also have electric potential energy associated with more than two charges. What we have to do is imagine grouping all of the different pairs that we could create with our system. I've used an example here with just 3, but you could also have 4, 5, or any number of particles and group them in pairs. So we would write an expression for the potential energy as the sum of all of the pairings. So for example, we would have K times Q1 times Q2 over the distance separating them. Now notice you don't square that. You're used to squaring it because it looks a lot like the Coulomb's law equation, but in potential energy it is not squared. And then we'll group 1 and 3 together. So we would call this K times Q1, Q3, and the distance separating them. Well, what is that distance? It's R12 added to R23. That's actually also the distance x. If you notice on the horizontal axis, we could just use x there. And then the final pairing would be 2 with 3. So it's K, Q2, Q3, and the distance separating them, which is R23. Now let's consider the sign of each of those terms. Q1 is a positive charge, as it looks there in red, and 2 and 3 are negative charges. So whenever we group oppositely signed charges together, we're going to introduce a negative sign. That would be this term here, Q1 with Q2, and it would also be Q1 with Q3. So those will be our negative terms, and then we're going to have a positive term here with the last one. Two negative charges, when you put two negatives and multiply them, you're going to get a positive. So it's possible we could have enough negative to counteract the positive, and we could get a total of 0. It's not unusual at all to have a potential energy associated with a system of objects that's actually equal to 0. So I'll leave it to your imagination how many different systems we could come up with, but you're certainly going to do some practice with potential energy, and then we'll change our attention then to electric potential, which is a related concept but not identical.